Welcome back to Chapter 1.2, Expectations, Variance, and Covariance as Geometry, Part 3 of 9. In Part 2, we defined variance and covariance and learned to read covariance like a story. Now we make it concrete with a 4-cell example, computing a covariance by hand. Then collect 3 of the 4 algebra rules that carry almost everything in this book: scaling, bilinearity, and symmetry. These rules all follow from the definitions, plus linearity of expectation. A number before any more Greek. Suppose 2 assets each return plus 10% or minus 10% with the 4-cell joint distribution shown. The diagonal cells, where both move the same way, each carry probability 0.4. The off-diagonal cells, where they move oppositely, each carry 0.1. Each asset is up half the time and down half the time. So the expected return of each is 0, and the variance of each is just the expected value of the return squared, 0.10 squared, equal to 0.01. For the covariance, we need the expected product of R1 and R2. The 2 same direction cells contribute 0.1 times 0.1 times 0.4 twice, giving plus 0.008. The 2 opposite cells give minus 0.002. Adding gives the expected product 0.006. Since the means are 0, the covariance is 0.006 positive. The diagonal weight makes the assets move together. We reuse exactly this when we estimate covariances from real data, where probabilities become observed frequencies. Now, 3 algebra rules, each following from the definitions plus linearity. First, scaling. The variance of a times x is a squared times the variance of x. The square is because variance is built from squared deviations. Doubling x quadruples its spread in squared units. And a constant shift does nothing. The variance of x plus a constant equals the variance of x, because adding the constant moves x and its mean by the same amount, leaving every deviation unchanged. Second, by linearity, covariance is linear in each argument. The covariance of a times x plus b times y with z equals a times the covariance of x with z plus b times the covariance of y with z, and likewise in the second slot. Constants slide out, sums split apart. This is the property that makes covariance behave like a product, and, as we will see, like an inner product. Third, symmetry. The covariance of x and y equals the covariance of y and x. Order does not matter. To summarize Part 3, we computed a concrete covariance of 0.006 from a 4-cell table, exactly the arithmetic we will later run on real return histories. Then 3 algebra rules. Scaling pulls out a squared constant and ignores shifts. Bilinearity lets covariance split across sums and pull out constants in each slot, behaving like a product. And symmetry says order does not matter. In Part 4, we combine these into the 4th and most important rule, the variance of a sum, and meet the cross term, that is the entire seat of diversification.